Welcome to this presentation for a simpler model for recovering Superpoly on Trivium. This is a common work between Stéphanie Delon, Patrick Derbez, Charles Predon, and myself. First, for some context, cube attacks were introduced by Dinir and Shamir at Eurocrypt 2009 as a variant of higher-order differential attack. The idea for a stream cipher F is to compute the sum of f over all the possible values of a chosen cube, and this will reduce to a polynomial named the superpoly. So the main goal of the cube attack is to recover the superpoly. The division property was first introduced by Todo at Eurocrypt 2015 to retrieve some partial information of a polynomial. Then it was upgraded to the exact division property at Eurocrypt 2020, and this version was able to retrieve the complete superpoly. The same year, at AsiaCrypt 2020, the monomial prediction was presented to retrieve also the complete superpoly. First of all, any Boolean function can be described as a big polynomial called the algebraic normal form ANF. And since most stream cipher can be described as a Boolean function, then if we have some information about the ANF of a stream cipher, then we have an information about the stream cipher. To set up a cube attack, we first need to choose a cube. So a cube is a set of chosen variables in the initialization vector of a stream cipher. Then the superpoly is the subpart of the ANF where each monomial contains at least the cube. For example, if my cube is v1, v2, v4, and we find in the ANF the monomials x1, v1, v2, v4, x1, x5, v1, v2, v4, and v1, v2, v4, then the superpoly is x1 plus x1, x5 plus 1. And the goal is to get the superpoly. To get the superpoly through all the round functions of a string cipher, we'll need to propagate each monomial. For example, here I have two functions, and I will propagate the monomial x1 through this round function. First, for the first function, we see that x1 appears in the polynomial of the monomial y1. We see that x1 appears one time in the polynomial of the monomial y2, and we see that x1 appears also one time in the polynomial of the monomial y1, y2. So we say that we have a monomial trail from x1 to y1, we have a trail from x1 to y2, and from x1 to y1, y2. Then we propagate this monomial through the second round function. So in z1 we have y1, y2, so we have a trail from x1 to z1. So this means that in the output bit z1 of my little example cipher here, we know that the monomial x1 will appear. But for z2, it's slightly different because we have y1 plus y2. So we have two trails from x1 to z2. And since we are in f2, the plus here is XOR, so the two monomial x1 in this polynomial will cancel themselves. So in the end, to retrieve the superpoly, we want to find all the monomial trails of the superpoly, but we want to consider only the odd trails, because if we have an even number of trails for a monomial, then we will have some monomial cancellation. The previous method uses bitwise constraint to model this problem, like copy and XOR, and this is the example of the two-round function of earlier. And in this paper, we propose to model this instead in a graph model. So there is a one-to-one mapping from this model to this model, but the main difference is that the graph-based model focuses on the transition between the bits, the edges, and the division property focus on the bits themselves. So we have a graph model that is simple and usable in MILP or constraint programming. With this graph model, we can add some doubling pattern to reduce search space by cutting the even trails. We can use some previous works on the arity approximation to have a good solver strategy to reduce the solving time. And in the end, we are better and faster than the previous methods. We are better because we have half to 80% event trails that are cut from the solution pool, and we are consistently 6 to 60 times faster than the previous methods. Now I will present how to model Trivium as a graph. So Trivium is a stream cipher with 3 registers that I will call A, B, and C. The three registers are initialized with the key on register A, the cube on register B, and some constants on register C. Then the registers are updated with the following functions. The first bit is computed with this formula, and all the other bits are shifted. Once we have produced enough initialization rounds, we will compute the output bit Z. So to have Trivium in a graph, we will model this equation into an automaton. So here, the nodes A, B, C represent the first bits of each register A, B, C, because this is the only bit that is interesting. This is the only bit with an equation. And all the shifts are on the edges. For example, if I am on the first position of the register A and I take the looping edge, I stay on the register A, I will be sent to the 69th position of the register A. So we'll have to wait 69 rounds to be shifted to the first position again and to take another transition. From A, we can also take a transition to the register C. We have 3 possibilities: the smallest arc, the doubling arc, and the longest arc. And Trivium is very symmetric with a specific structure, and we can see that the long arc is always 1 shift and 2 shifts more than the doubling edges. This means that if I take the long arc from A to C and then the doubling edges, from C to B, it will end up to the same nodes on B as if I took the doubling edges from A to C and then the long edge from C to B. So we see that there are already some solutions that are similar. So we will develop this automaton from the output bit we choose to the first round of Trivium. So this is an example. We have the output bit up there, and the leaves here are the first round of Trivium. So we have in blue the cube bits, and in red here we have one monomial from the Superpoly. So this graph is a solution and represents a trail for the monomial x16. So we want to find all the trails from the output bit to this monomial with this cube, and we want to know if we have an odd number or an even number of trails. But we could also try to constrain earlier in the graph the doubling patterns. So as I said earlier on the automaton, we have a long double pattern. If I take the doubling transition, then the long transition, I will end up to the same leaves than if I took the long transition, then the doubling transition. But we have several more patterns like this in Trivium. For example, the pattern we use the most is the 3 consecutive bit pattern. If I have 3 patterns, 3 bits active at 3 consecutive rounds on the same register, then if the 2 side nodes take the doubling transition, then the middle node cannot take the long transition or the doubling transition because it will lead to the same leaves at the end. But we have some more complicated patterns. For example, the looping pattern. If I am on a register and I choose the looping edge, I stay on the same register. Then if on all the branches of the subgraph I return at least one time on register C on all the branches, I could take the looping edge at the end and not at the beginning. I will end up to the same leaves. But this pattern there are a lot of combination of these patterns, so it is not practical for the model because this will add too much constraints to the model. We also have some easier constraints, some easier pattern to constrain. For example, the cycle pattern. If I take a cycle from C and then I go back to my first register here, C, and then I take an edge that is not an edge of my cycle, then I could take this edge first and the cycle after. This pattern is simpler to constrain, but is not oftenly used in our case because we want to search for big cubes to have the smallest superpoly possible. And to reach the big cube, we'll need to use the doubling transitions that are not used at all in this pattern. So this is not really useful in our case. So this asks the question of whether a pattern is useful or not to add in the model, because some patterns are simple but not very useful, some patterns are really hard but very useful, and some patterns are great. But there is another problem, and this problem is the overlapping of patterns. For example, for the 3 consecutive bit pattern, if I take into consideration 4 consecutive bits, then I will apply my constraint on 3 consecutive bits with the 3 right nodes here, as the red edges in my example. So I will constrain these 2 solutions, and then I will take into consideration the left 3 bits with these red edges here, and I will constrain another 2 solutions. So I think that I have constrained 4 solutions, but in fact I've only constrained 3 because the 2 left patterns here are exactly the same. So I canceled 3 solutions, which is a big problem because I break the parity and I won't find the right solution, the right superpoly. Sorry. So to prevent this overlapping, we add to the constraint of the 3 consecutive bits some information about the 4th bit. So this is the constraint for the MILP model for the 3 consecutive pattern, and we add at the end one additional case with the 4th bit. So this is sufficient for preventing the overlapping of the pattern 3 consecutive, but there are more complicated overlapping. For example, if we have multiple patterns at the same time, they could cancel themselves because of the overlapping, and we think this is a really hard question. So in our example, we took only the 3 consecutive pattern with this constraint to prevent the overlapping, and as a result, we find that without any doubling constraint, we find the exact same solutions than the previous methods, which is normal. But with the pattern 3 consecutive, we find less solutions, and we know that if we could use more patterns, we could find even less solutions. Now we'll talk a little about the solver strategy and the arity of the cube. So the Trivium is a very big problem, and the solver cannot solve it without a strategy. So the previous methods were using some strategy. For example, the division property uses a hot start. They find one solution and then they restart from the beginning of this solution to find all the solutions that have the same beginning. And since Trivium has the form of like a tree, this is a really good strategy because a lot of solutions will share the same beginning. The monomial prediction method is using a divide and conquer strategy. They cut the first rounds and then they solve all the sub-solutions. This is a method that is slightly similar. But this method tells us that the basic MILP strategy is not sufficient to solve the Trivium model. But in Trivium, we know some things. We know the structure of Trivium, and we can use it to have a good strategy in the solver. To use this strategy, we'll use the arity approximation introduced at Crypto 17 by Liu. The idea is for each node, we will try to approximate the number of cube bits we can reach from this node. And they show in the paper that to have a good approximation, we need to take into consideration 2 rounds of Trivium, because if I take the doubling edges twice in a row, for example here, I will count the arity of this node twice in the further node if I don't take care of this. There are arity redundancies and two doubling transitions. So we will use this formula as to have a good strategy. So for our strategy, the first step is to compute the arity approximation with dynamic programming for the cube we choose. And then we use a solver strategy. The solver have multiple options to help define a strategy. For example, with the solver Gurobi, we have the option var hint val that let us say which edge we want to focus on. So we want to focus here on the doubling edges because we know that the hard part of Trivium is the doubling edges. And then we set a branch priority on these doubling edges to focus on the big arity edges, because if there is a big arity, we know that by taking these edges, we will most likely end up to a solution. And with this strategy into the solver, we don't need the divide and conquer that we're using the previous methods. In the end, as a result, we first see that the CP model does not scale well because Trivium has not a really highly combinatorial structure. In fact, there is only one doubling transition, one multiplication. But we see that the MILP model performs very well and is consistently faster than all the previous methods with less solutions, as I said earlier. As a conclusion, we propose in this paper a new graph model that enables the using of doubling pattern as constraints to reduce the number of even trails and even solutions. That this graph model also enables the usage of an arity approximation to have a good solver strategy to reduce the solving times. And then at the end, we have a faster MILP model with less even trails. For the open question, the first big question is how to prevent the multiple pattern overlapping, because we want to use as much patterns as possible, but the multiple pattern overlapping we think is a really hard question. We could also strengthen the solver strategy with other Trivium features than the arity. Maybe there is some structure we can utilize here. And we could also apply the graph method, the graph model method, to other ciphers. Thank you for your attention and your listening.